Thank you, David, and thanks to the organizers of Strings 2017 for the hospitality. So I like to think of our understanding of string theory as being a kind of tripod with three legs. The oldest is perturbative string theory, which has always been miraculous looking. The second is the understanding of non-perturbative dynamics, where you can actually say something about what happens for strong coupling. And the third, which appeared just a few years later, of course, 20 years ago this year, was the anti-de Sitter conformal field theory, or gauge-gravity duality, which we're talking about in this session. Now, critics used to be fond of saying that string theory is just perturbation theory. Well, what is it that convinces us that this is wrong? That there's an exact theory, even if we don't understand it yet? Well, first, the successes and also the beauty of the perturbation theory were always strong indications that it had to be for real. And secondly, the ability to get a sensible and delicately consistent understanding of strong coupling made the contrary hypothesis even more implausible. But the clincher, perhaps, is the ADS-CFT correspondence, which gave a non-perturbative formulation in many situations. Although it's an enigmatic formulation that in many ways still baffles us today. That being why, as Igor just said, ADS-CFT has been an amazing source of new ideas for 20 years. So I would claim that many traditional arguments became obsolete roughly a generation ago when the ADS-CFT correspondence was discovered, though some of these obsolete arguments are still heard today. Now, when I say that many traditional arguments became obsolete, I'm referring to, as I've said already, the question of whether string theory exists beyond perturbation theory, the question of whether it admits a background independent formulation, because at least with negative cosmological constant we have one, a formulation that only depends on the asymptotic background, as should be the case in quantum gravity. And there are other examples we'll come to in a moment of traditional arguments that became obsolete. Now, as Igor discussed, ADS-CFT has also had a major impact, at least in spirit, on the way we think about strongly coupled gauge theories, and especially QCD. So, okay, ADS-CFT is 20 years old, but twice as long as that, and even a little bit more. Hoof proposed that QCD in the large n limit is equivalent to a string theory, or actually, as he expressed it at the time, equivalent to a dual model. But until 1997, this idea was kind of a tantalizing mirage at the fringe of what one could imagine. It lived in a land of dreams, which is where, at least in my opinion, Monton and Olive duality had been living until a few years before. So it was in 1997 that the idea of strongly coupled gauge theory as a string theory left the land of dreams and emerged as reality. And this reality, at least in spirit, has given us a better understanding of QCD, with the understanding that many four-dimensional gauge theories really are string theories in the large n limit, and you can use this to make interesting new models of confinement and chiral symmetry breaking. So, at least in spirit, QCD is an area where ADS-CFT shed some unexpected and long-awaited light and gave us a richer understanding of strong coupling dynamics in gauge theory, and a lot more confidence that QCD is equivalent to a string theory, although we don't still know which one. We've had a few talks at this conference that are related to that question. More broadly, ADS-CFT made it clear that string theory is an unavoidable part of the study of ordinary quantum field theory. Because you could be minding your business studying a gauge theory, and it has a large n limit that's actually equivalent to a string theory. That's a loose way of talking. The precise statement is that the gauge theory is equivalent to a string theory, with 1 over n as the string coupling constant. So it came as a shock to most of us to learn that string theory was part of the study of standard quantum field theory, though clearly there was some schizophrenic outlook on the world because of that, because given the long suspected link between QCD and string theory, probably it shouldn't have been such a shock. It had been predicted 20 years later, but it still was a kind of a shock when it turned out to be true. But I'm not claiming that QCD is an area where ADS-CFT made traditional arguments obsolete. And the reason I'm not making that claim is that there wasn't any notable group of physicists or pundits who were criticizing the idea that gauge theory was equivalent to a string theory. This notion, for us, was on the horizon in the land of dreams, but it wasn't on the radar screen of the critics and pundits. Now, black holes are an area where ADS-CFT actually did make some traditional arguments obsolete. So for one thing, it became extremely clear that black hole evaporation and decay can occur in the framework of conventional unitary quantum mechanics. But more broadly, I think 20 years ago, Hawking evaporation and the whole complex of ideas around it were the dominant point of view, but there was certainly skepticism at the margins, and even some of the practitioners might have 20 years ago still expressed some misgivings about it, or at least doubt. But I think ADS-CFT has made any of these doubts obsolete. It's one thing to give abstract arguments that when a black hole captures an incoming body and then relaxes to equilibrium, that's analogous to ordinary thermalization of an everyday object at home or in the lab. But it's quite another thing when physicists in a variety of fields studying questions of thermalization find that modeling it by black holes is actually useful. So in a variety of fields, from heavy ion physics to condensed matter physics, this is now happening. In fact, this started happening in the first half of the 2 decades we're reviewing. So when physicists in various fields find that this interpretation of black hole physics is actually useful for modeling difficult problems in their fields, some of the traditional questions hanging over the subject became obsolete. So a typical example here is the crossover between quantum and thermal behavior near a quantum phase transition, which is nowadays actually usefully modeled in terms of black holes. And I think we'll even hear about it from later talks in this panel. And there were earlier talks in this direction at the conference. So what I've, in a sense, surveyed so far is the first decade of ADS-CFT. I'll say less about the second decade, but I'd like to say that one of the reasons that the subject didn't run out of steam and that the second decade, in a way, was as exciting as the first was a whole complex of developments that, in large part, started with the Ryu-Takanagi formula for entanglement entropy. Of course, there were other important sources of new thinking about entanglement entropy, lots of them. We actually heard about one in the Gong Show, but I can't really review this now. But the upshot is that we're living in a fascinating period with lots of fresh thinking about entanglement entropy, quantum information, and the relation to black holes, quantum mechanics, and gravity, and more. So there are lots of new ideas and loose threads that give at least some hope that the third decade of ADS-CFT will be the most exciting. So I'm not going to try to review this current period, but I'll conclude by pointing out a couple areas where there's work to be done. So one obvious point is that we've learned a lot about non-perturbative background independent descriptions that are on the boundary, or they're holographic descriptions. But our understanding of how to give a bulk description of string theory / quantum gravity has lagged behind. Even when we have what one would hope would be simple toy models like Vasiliev theory, or the dual of Vasiliev theory, or the SYK model, we only have a hazy idea of the bulk physics. And progress has lagged on new non-perturbative understanding of more conventional string backgrounds. So one way or another, we're in need of something, clearly. maybe new bulk descriptions, or maybe part of wisdom would be a better understanding of why it's hard to find new bulk descriptions. And maybe what we should be looking for is different from what we traditionally think we should be looking for. But anyway, we're in need of something. And to illustrate another idea where progress is called for, I'll offer the following picture. So here we're imagining an asymptotically ADS space. Here's infinity. Here's r equals 0. And there's matter in it, although I haven't tried to draw the matter. And matter rattling around in ADS space is likely to eventually collapse to a black hole. And likewise, if you evolve it into the past, there would have been a past singularity. So I've drawn two pictures. Here, the past and future singularities don't intersect. There's a nice initial value surface that's outside of any singularity. And this is the situation where the boundary theory is clearest. Here I've drawn the opposite situation, where there's a region behind both past and future horizons. And this is then rather mysterious because there's a region that you can't see or influence in any way from the boundary, at least according to the classical description. And if you try to think about this situation, you run into paradoxes, as discussed, for example, in this paper. Because if you try to estimate how many quantum states there are behind the horizon, not just behind the horizon, but in this region that's behind both the past and future horizon, you find that there are far too many of them. So this picture seems problematical in ADS-CFT, and maybe we could learn to understand it better. And the speculation I'd have liked to offer, I'm hesitant to offering it because I'm not sure it's viable given all the examples we know, but the speculation I'd have liked to offer is that such spacetimes correspond roughly to unstable saddle points in the large N theory, or maybe saddle points in the large N effective theory that aren't actually on the appropriate integration cycle, or whatever that means, of the exact theory. But I'm not really sure if this point of view is viable, given the many examples in the literature that raise versions of this puzzle. So I'll just leave this with a question, and thank you.